Do you know, the vast majority of vehicles have suspension operation that is less than ideal for any given operating condition. This applies to cars, trucks, motorbikes, even hand-built clubmans. Semi-active suspension can improve the performance of these vehicles by providing suspension operation that is close to optimal. The benefits of semi-active suspension become clear when you look at the operation of suspension and the construction of regular passive suspension dampers. So different road disturbances require different damping values. The damping setting most appropriate for a speed bump-like disturbance is different to what is most suited to accelerating or cornering conditions. The design of passive suspension dampers limits their ability to change to suit the conditions. Dampers used in suspension are typically fluid-filled devices with an internal piston connected to one end of the damper. Energy is dissipated by restricting the flow of fluid past the piston. There are various methods to restrict the fluid flow. Some of them remain constant throughout operation, others have variable damping force, which will change based on force or velocity. Either way, these both suffer the same problem, which is the components that affect damping are internal to the damper unit and cannot be changed throughout operation. Because of this, compromises are made when allocating a damping value. These compromises will allow reasonable performance across most terrains and conditions, but they're never perfectly suited to one type. For motorcycles used in off-road racing, these compromises will be more noticeable. This is because bikes experience larger disturbances than road-going vehicles and also experience more regular and aggressive terrain changes. So the rider of the bike also contributes to this. So the rider can be sitting or standing, it can be leaning over the front of the bike or hanging off the back. And since the mass of the rider is not that different to the bike, it has a noticeable effect on dynamics. This is where semi-active suspension can improve a vehicle's operation. Semi-active suspension is a type that can change damping values during operation in response to disturbances and conditions. A suspension controller will take system information and from there determine the operating conditions and then decide on the most appropriate damping value. So my project was to see if semi-active suspension could improve the performance of an off-road racing motorcycle. This is done by designing and then testing in simulation a control system for a semi-active suspension system. So the key tasks to complete were develop a model of the motorbike. This model is needed for simulation and then in control design. I had to validate that model just to confirm that it is suitable for simulations. And identify a control objective. So this is to find out what conditions give the best performance for the bike and how to implement control to achieve those conditions. Lastly was design the controller. So this is develop a controller suitable for semi-active suspension. It was then applied to the model and tested for comparison against a standard bike. As this work was aimed to assess suspension operation, some simplifications have been made to the motorcycle model. Usually riders remain centred over the bike, which means forces in the Y direction, so Y direction for a coordinate system that is fixed to the bike and will rotate with it. Forces in the Y direction will be minimal. Then forces in the X and Z directions are going to have the same effect on the bike regardless of the roll angle. So with that assumption, the bike model was reduced to 2 dimensions. So that's the bike model. Got the chassis mass, then front and rear unsprung masses. So both the front and rear suspension contain a spring, a damper and a controlled variable damper. The model shows that the rear suspension is connected directly to the swing arm. It's not actually the case. It's connected through a linkage that gives a rising rate suspension operation. But rather than include this into the model, expression was determined to represent the kinematics of the linkage. So the model has been formulated using the Euler-Lagrange equations of motion with virtual work terms for the front and rear suspension, the wheels, external input forces and the rider input forces. So these make allowances for the changing operation of the suspension. So as the suspension changes, you'll have compression and rebound damping. There's bobbing resistances as it nears the end of travel. and also for the effects of nitrogen pressure inside the rear shock. So while accelerating, there is a tension in the chain. Those forces have been allocated, as well as the reaction torques due to braking. So while the model is two-dimensional, a cornering motorbike are going to have roll angles other than 0. To be able to simulate this with a 2D model, I've used a variable acceleration term that represents the magnitude of the gravity and centripetal forces. So I was able to get my hands on some data from the KTM factory in Austria, which is what has produced these plots. So these show the damping forces of the front and rear suspension from one of their factory bikes. So the plots on the left show the damping forces, while the ones on the right show the calculated damping coefficients. It's pretty easy to see that the damping here is not linear. So to give a more even comparison of the semi-active to the standard bike, polynomial expressions were developed to sort of fit this data and then applied to the passive bike. The rider is modelled as a single mass, which is connected to the bike via spring dampers to be the arms and legs. Each arm and leg has a force actuator in it, which will allow the rider to be controlled to somewhat imitate a real rider. Control is done with a simple PID control, just to try and minimise the acceleration of the rider. Also, by supplying constant forces to these force actuators, you can move the position of the rider on the bike, so different disturbances the rider will sit forward or back. To determine the validity of the motorbike model, the intention was to compare the simulated response against that of a real bike. I was unable to find suitable data to do this though, so instead a number of small tests were used just to assess different parts of the bike. One of which was simply comparing visually the simulated response of the bike against some riding footage. The two green gauges at the bottom there, they show the suspension position. The next bar over, the FRACC, that is the driving force coming from the rear wheel. So the main thing to notice here are the similarities between the suspension displacements. So for both bikes you will see that as the front wheel hits a bump, the suspension will displace roughly 50%. Then as the rear wheel comes over, it'll be about 70 to 80%. So just for reference, for the real bike there, when the suspension is at maximum travel, the wheels all but touch the mudguards. The control system developed is a non-linear model predictive controller. Predictive control can provide optimal control inputs by using an iterative propagation process that will allow the controller to verify that the control inputs will ultimately lead to desired system response. So non-linear MPC was chosen for this application as it has a number of features that are suited to semi-active suspension. So it will accept the non-linear model dynamics without needing approximations. Constraints. So not just the non-linear MPC but linear as well allow you to define constraints. So these can be for maximum suspension displacement, actuator limits or slew rates. So the non-linear MPC allows these constraints to be non-linear. This is an important one for semi-active suspension. As a semi-active system implements control only through variable damping, and because a damping can only dissipate energy, semi-active suspension is unable to supply any energy to the system. So firstly, this means that the damper will have to have some velocity to be able to give any control. And secondly, that control inputs can only oppose the velocity of the damper. To identify a control objective, I first had to find what conditions led to the best performance for the motorcycle. So to do this, I set up a simulation where the controller had access to all states, including the external disturbances like the road inputs and then the rider inputs. So the bike was then run across a varying terrain profile for a set interval, and using various non-linear programming methods to find control values that would maximise the velocity of the bike. So this optimisation was completed a second time, but this time was to try and maximise the horizontal displacement of the bike. Throughout this, the values and output of each iteration were logged, so I could analyse the results at the end of it. So of the top results, the ones that caused excessive accelerations for the bike or had other undesirable behaviour, they were filtered out, and then the remaining top results were applied to the controller and then simulated again, so the output could be graphed and compared with the passive motorcycle. So this comparison showed that the bike was fastest when the fluctuations in the tyre normal force were minimised. Another optimisation was then completed to determine which system state should be controlled to minimise the fluctuations in the tyre normal force. So from this it was found that the tyre normal force was more consistent when the vertical acceleration of the motorcycle was reduced, also by reducing the suspension displacement, which gives the max available travel, and to a lesser extent the vertical velocity. Interestingly, the angular velocity and acceleration had almost no impact on the tyre normal force. Now knowing which states were important to be controlled, the controller was reconfigured to only have access to the variables it would normally have access to during operation. Then from here, the controller was tuned. So to tune the controller, again, it's done with an optimizing function. This time the error weightings were tuned to maximize the horizontal displacement of the bike, in a set time period. This did have a tendency to cause the suspension to bottom out, which would then lead to a large acceleration for the bike. To address this, a variable error weighting was used for the suspension displacement. So as the suspension displacement increased, so would the cost. This video here shows the passive bike compared to the semi-active bike in a small race. The gauges at the top there, the green bars will show the damping coefficient provided by the controller, and the blue bars show the force due to damping. On the bottom there's the force from the rear wheel again. Now this force is determined as a function of the normal force at the rear tyre and the tyre friction coefficient. To make sure the race was even, the standard bike was tuned for the track. So tuning meant finding optimal damping values that would minimise the time to reach the finish. To preserve the shape of the damping curves previously shown, the tuning variables were scaling factors on the polynomial damping expressions. So there's one for the front and rear compression and rebound damping. So the scaling factors produced from this were pretty close to 1. So providing that my model is accurate and a reasonable approximation of a bike, it shows that the damping values of a factory bike are actually pretty good. At the first disturbance, you can see the difference in the two bikes. The semi-active bike will lower the compression damping, which allows the wheel to react to the disturbance while imparting less vertical momentum to the bike chassis. Here the standard bike, unable to do this, it sees a brief period of increased driving force, but at the cost of increased vertical momentum. As the disturbance levels out, this positive vertical momentum reduces the traction at the wheels. Then as the disturbance is decreasing, with the road pulling away from the wheel, the suspension of the standard bike, again being unable to change damping values, it will extend slower than the semi-active bike. As the semi-active bike can reduce damping, the suspension can be made to extend faster, which will give the wheel better contact with the ground and provide more traction. The results show that the semi-active suspension is effective, though there were a few aspects that were omitted or not taken into account that may affect these results. Things like assuming that the two-dimensional model was sufficient to characterise the suspension operation, or that latency in the variable damper is small, or even that the controller can run in real time. But as the purpose of this project was to see if the performance of an off-road bike could be improved with semi-active suspension, even if these assumptions reduce the performance increases, semi-active suspension will still have a positive effect on the bike.